this afternoon session. Our first speaker is Sukhorukov, and he's going to tell us about the theory of fractional quantum called interferometers. Eugene?
Thank you very much for the invitation to this nice, cozy place. I will be going to present a theory of fractional quantum called interferometers with some disclaimer. First of all, I am a physicist, so I was mostly responsible for the physical part of the project. And if you have complicated math questions, I hope for the support of Jurg, my collaborator on this project. And also, let me mention that most of calculations are done by my student Ivan Levkivsky. Second disclaimer is that this is not a recent work. It was published about 12 years ago, and I might have forgotten some details of it. Nevertheless, I think I didn't have a chance to present it before, so I will be happy to talk about this today. And second thing is that recently there was an experiment, so only now actually experiments came, and actually it's a quite an interesting experiment with which answered some questions, but with also kind of open questions. And so field is actually, getting again mainstream, so it's interesting to discuss this physics and mathematics. Okay, so let me tell you that I will present the theory of interferometers, electronic interferometers, which are based on H states. Basically, I will speak about mostly Mach-Zehnder interferometer, where beams propagate in one direction. So this is like optical scheme of Mach-Zehnder interferometer. Beams of light propagate through semi-transparent mirrors, are reflected at other mirrors, and there are two paths from the source to the detector. By changing position of mirrors, one can observe interference signal and interference fringes in intensity. So so the idea would be to do similar experiment with electrons, with H states, which are chiral states that propagate in one direction, like beams of light. But the difficulty is that, well, it's not easy to make such to repeat such optical scheme in an electronic system. And what people do in experiment, they prepare two-dimensional system in the form of carbon disk. So it means that they remove part of material here and outside, and they create such a disk or system which is topologically equivalent to such a disk. And then they use massive piece of metal in order to make an electronic contact to H states, and such pieces of metal play a role of black body in quantum optics. So then, for instance, outer H state propagates counterclockwise, inter H propagates anti-clockwise, and then there are two paths to go from source to drain, because one can also attach or prepare some quantum point contacts where H states can be partially backscattered or transmitted. These point contacts play a role of semi-transparent beams. So then the current accumulated from the source to the detector, and because there are two paths like this or like this, up, they create a kind of loop, and then one can change magnetic field or deform this H in order to observe interference pattern and in the conductance of the system. This is a bunch of experiments where this type of system was first introduced and then experimentally used in order to study Aron-Bohm effect and a lot of other effects associated with it. So here's a micrograph of the system. You see that it doesn't look like exactly this carbon disk, but it has all the properties of it. So topologically it's equivalent to carbon disk. Now let me tell you that the most difficult part is to make an oblique contact inside such a system. The experimenters do.
What is the difference between Mach-Zehnder and Fabry-Perot?
Okay, so very important question. Thank you for this question. In Fabry-Perot interferometers, beams are shown back. So there's kind of backscattering process. So you can think about kind of closed loop, which is connected to external leads by tunneling. And then if beams go back, then this is called Fabry-Perot interferometer. And in Mach-Zehnder interferometer, there's no way they can go back. For instance, in this system, So when you go there, so there's no possibility to return to the source because the path is interrupted by a moment contact, which is like it's a huge reservoir where electrons enter and never leave back. So never go back. So the propagation is in one direction only. So like in this scheme, so the beams propagate in one direction. So why is it important physically? Because in fabricator interferometers, which present a localized system, isolated localized system, then which you attach weakly to reservoirs. In such a system, the Aronoff-Bohm effect can be confused with Coulomb-Blanquet effect. You cannot differentiate between Coulomb-Blanquet effect and Aronoff-Bohm effect. Coulomb-Blanquet effect, it's where, because the system is isolated, charge is quantized, and you see oscillations of the conductance just because charge is quantized, and this quantization is partially suppressed. So you cannot differentiate with Aronoff-Bohm effect. That's why this was motivation, although it's very difficult experiment, to prepare such systems where system is not closed. It's attached to reservoirs, and charge is not quantized because of this. It's an open system. Look at this system, for instance. It's an open system, and the number of particles inside is not quantized. So it will be pure Aronoff-Bohm effect.
So charge is quantized perhaps, but not conserved.
I do not agree. Because in fact, charge is always conserved in some sense, but not quantized in the sense that, for instance, quantization is reflected in oscillations of conductance if you change, for instance, if you deform the path, if you change gate voltage, what is called gate voltage, you change average number of electrons, and then in conductance you see oscillations. That's what people call quantization of charge. Now, in open system, such oscillations do not exist. They can appear only as a Aronoff-Bohm effect.
Usually, normally charge quantization means that there is a cross-section and you count how many electrons come through. Obviously, it's integer.
Not necessarily. Quantum mechanically, you can have superposition. And so that in average, you will observe not an integer number of electrons or other particles. So exactly, it is this superposition which destroys quantization of charge in Coulomb-Blanquet effect. And quantization, just oscillations of the conductance will disappear with temperature, for instance, or with transparency. So for an open system, if no backscattering, you will not see such oscillations at all. Quantum fluctuations will destroy, in average, such oscillations. But of course, if you measure noise or correlation function of current, then you can observe, of course, such quantization. Okay, so let me also briefly mention that there is such air bridge. So excuse me for one. The air bridge here, which creates non-move contact. It's a piece of metal which goes up and down, and then makes a connection to the system inside in such a loop. And then these are point contacts, and these metallic pieces, they deform electron gas inside and deform the path, so that one can see oscillations, which are kind of Aronoff-Bohm oscillations, because you change flux, magnetic flux for the loop. Okay, so here's my talk, content of my talk. I will first introduce, make a short introduction where I will mention Van-Froelich theory of Coulomb H states. Then I will present spectroscopy, how one can do using interferometers, spectroscopy of quasi-particle excitations, why it is important. Then I will mention that in fact there is a certain statement which is called Byers-Yang theorem, but it's not a really theorem, it's a very simple intuitive statement, physical statement, which tells you that there is a problem with this spectroscopy of quasi-particle excitations. And then I will mention early works which tried to resolve this Byers-Yang paradox. Then I will briefly present, not very briefly, present microscopic theory of quantum Hall interferometers, where we tried on a microscopic level to resolve this Byers-Yang paradox. And then I will conclude. Okay, so from the point of view of Van-Froelich theory of H states, they are considered as excitations as weak deformations of H of quantum Hall liquid, which is incompressible liquid, but at H it can be deformed, and such oscillations can propagate currently in one direction, and they are described by density operator, which is derivative of phase operator, and this phase operator has canonical commutation relations. From these phase operators, one can construct a quasi-particle vertex operator, which changes number of quasi-particles in the state. And it's a local operator which commutes with total charge like this, so that the charge of this quasi-particle operator is 1 mm, at filling factor 1 mm. So it's a fraction of electron. And then, of course, one can also construct, by taking this quasi-particle operator to the power of n, one can construct electron operator. Okay, so electron operators have fermionic commutational relations and have charge equal to 1. Now, the first problem is to connect this to Laughlin theory, or this theory, effective theory, to Laughlin microscopic theory. This is one of the problem of this project. And second is to try to resolve Byers-Young paradox. And let me already tell you now that I think we managed to resolve this paradox. So now, what was our initial point of this project? We wrote a paper with Jurg, with Alexei Boyarsky and Ivan Levkivsky, where we proposed to use interferometers in order to study scaling dimensions of quasi-particle operators. So imagine that at each, for certain minimal model, like for filling factor 2 over 3 or 2 over n, you have a certain number of minimal models which propose different lattice construction, basically, for the minimal model, where you have different quasi-particle operators with different scaling dimension. So we propose to measure Aronoff effect in conductance, oscillations in conductance, where in principle you can have tunneling of different quasi-particles. And then you can study the period of this oscillation, so you can single out contributions of different quasi-particles with different charge. And then you can study current voltage coefficient, basically the conductance, as a function of temperature or as a function of potential difference. And then you can read off scaling dimension of this particular contribution. And then you can compare it to minimal models. Here's we consider 4 minimal models, which are presented in terms of so-called K matrices, which are matrix of commutational relations for phase operators. And then for quasi-particles with different charge, like 0, 1 over 3, 2 over 3, 1, and electron quasi-particle, we found certain scaling dimensions which can be then compared to experiment. So I think, in fact, it was kind of abstract, complicated paper, but in fact, right now, there's an experiment where people, it will be published very soon, where people actually measure this. So it's actually physically related paper, so important paper. But at that time, we have been criticized for this paper because they said we proposed to observe quasi-particle oscillations with long periods, longer than electron period, related to charge of quasi-particle excitations. But in fact, our colleagues told us that it's completely wrong, just because our statement, our calculation contradicts Byers-Young theorem. So let me then formulate Byers-Young theorem. So if you have quasi-particle charge like 1 m, then associated Aronoff phase will be 2 pi phi over m phi naught, where phi is total flux through the loop, and phi naught is flux quantum. And you expect periods of oscillations, Aronoff oscillations, with period equal to m times phi naught. But in fact, this contradicts to a certain statement, which says that in any electronic system, you can observe only periods equal to phi naught. Where does this statement come from? So think about such a Mach-Zehnder interferometer. You thread a singular flux for it and change it continuously. Then there are two effects. When you change flux, first you introduce certain, by phi naught, you can introduce certain gauge field which can be completely gauged away. But when you introduce this continuously, this singular flux, there's another effect. Because you change magnetic field, you create electric field which pulls electrons away. It's like a Hall current, and you deform your system physically. So you go to another state. So basically, if you look at this carbide disk, you take a quasi-particle from inner edge and put it in the outer edge. So this is now an excited state. Yeah.
So a very naive question. So as far as I know, this Aronoff phase is a Berry phase. So it's related to adiabatic motion, but in what sense is this adiabatic? Now it's edge transport.
So could you repeat your remark? Okay, I understand the first part.
I would expect pick this phase if I would like capture a quasi hole in a trap and move it very slowly around the flux. But that's not what this is doing. This is edge transport. So why do you pick the very phase?
No, I think the phase which quasi-particles speak, it's a gauge field. So basically you can gauge away this singular flux, and quasi-particle vectors will acquire this phase shift which is observed in our normal oscillations. Does it contradict your statement? So once again, you have a field. When you insert a single flux quantum equal to basically flux quantum, this is pure gauge field. You can actually gauge it away, and quasi-particle vectors will acquire this phase field. And then the tunneling interacts at these points, which can be expressed in terms of quasi-particle vectors. The tunneling element or tunneling completer will require extra phase. That's what is called Aronoff-Bloom phase. Okay. So then you study in experiment conductors with oscillations as a function of this phase, as a function of magnetic field. So the idea of Bayes-Young argument is that if you insert quantum, then this is pure phase, pure gauge field, which can be completely removed. Quasi-particles will require a shift by 2 pi, so just 1. And so you remove really this contribution, but you go to excited state. Then in stationary limit, if you wait long enough, quasi-particle will tunnel back, and you go to initial state. Nothing changes eventually in the end, in a stationary limit. So it means that current will return back to its form, to its initial value. Therefore, you should observe electronic oscillations with period equal to not m phi naught, but just phi naught. So that's the statement of Bayes-Young.
It's relaxing at the end. It may take a huge time. You know, quantum Hall effect can be explained that way, that things come from out to the inside where you put the flux, and then it sits there, and but it's at an energy where the bulk has a gap and it will never make it back to the other end.
It depends. For instance, if we really study Aronoff-Bloom effect, then we always have a finite coupling at these QPCs. So here. Yes? So this quasi-particle can go back. So there are whole currents through the bulk of the system when you insert flux. They actually transmit quasi-particle charge from outer to inner, or from inner to outer edge. And then there's a tunneling at QPCs, quantum point contacts, which return quasi-particle back. So that in stationary limit, you shouldn't observe any quasi-particle oscillation, but only electronic oscillations. So, in fact, experimentally, you do not do this. Experimentally, you do not fret a singular flux, but you change, for instance, gate voltage or average magnetic field. But any model which proposes the theory of Mach-Zehnder interferometer should satisfy this statement. So that's experimentally you do something else, but model has to satisfy this statement.
Is it then a question of time scales, whether it
Yes, of course. If you consider just ground state, then a quasi-particle tunneling here opens the gap between, I will show it in the next slide, probably. Let me show, yes, here. So this is an argument of Taulis and Geffen of 1991, and Geffen and Taulis 1993. So that if you look at the spectrum of your system, which consists of, it consists of different branches, these different parabolas. Basically, it's basically constant direction energy. And then what happens is that if you have even weak tunneling, it opens the gap here between excited state and when you have intersection of parabolas. And if you change, for instance, flux continuously, and you do this slowly, then actually you follow ground state, which has an electronic period. It's another argument, which is not extremely relevant, just because it's a statement of ground state, but we have an open system. As I discussed, we do not consider Fabry-Terrell interferometers, we consider Mach-Zehnder interferometers. Therefore, this argument has to be renewed. So it doesn't satisfy us completely. But it shows the idea, what happens in stationary limit. So then there was a paper of Loh, Feldman, and Geffen in 2006, where what they did, they studied such Mach-Zehnder on the level of effective theory, as I mentioned before, but to each quasi-particle operator, they attached also what they call time factor. It's basically operator which has certain matrix element, where M is now number of quasi-particles. They acquire this matrix element, this phase factor. And if you do calculation for the average current, eventually you have to sum over all let's say for filling factor 1m, you have to sum over m from 1 to capital M, or so capital M from 1 to m. And then eventually if you sum over these phase factors, you get 0. So I don't go to details of this. I will, let's say if you took every quasi-particle pattern, if you attach such a Klein factor with simple algebra, that commutational relation gives you just a phase factor, then this phase factor, if you sum it over all degenerate states of a quantum Hall state with different number of quasi-particles, it gives you 0 eventually. So that's the argument. But in fact, this Klein factor is introduced by hands. So the idea of our calculations of our microscopic theory is to see whether such Klein factors exist or not. Let me tell you already now, in some sense they don't exist because they break gauge invariance. So in that sense, our microscopic construction is relatively useful. Okay, so then there was a paper which I completely don't understand. It's a paper of Ponomarenko and Averin. It's a very long paper where they considered fractional quantum Hall effect, started from weak electron tunneling, then they summed this tunneling completely and went to weak quasi-particle tunneling. So instead of weak electron tunneling, they considered limit of strong tunneling doing this summation. And they claim that there are Klein factors. But in fact, I have some questions to this paper which I'm not ready to discuss now, and it's not a completely transparent paper. So I think it doesn't satisfy us. Okay, so finally, I mentioned some experiments, ongoing experiments. One of them has been published. This is experiment of Weizmann Institute, or group of Weizmann Institute of They measured conductance of Mach-Zehnder interferometer, and they found indeed electronic period of oscillations. So in fact, in Mach-Zehnder interferometer filling factor 1m, there is no quasi-particle period. This is actually confirmed. So this statement satisfies Bayes-Young argument. The experiment rate has been confirmed. Okay, so let me now start to introduce microscopic theory. I will start with Laughlin type wave function. Then I will discuss classical plasma analogy in order to calculate matrix lengths. Then I will do a low energy projection. Then I will derive quasi-particle operator. And then we'll discuss the role of topology and how Bayes-Young is satisfied after such a low energy projection of Laughlin microscopic wave function. So let's start from Laughlin wave function. So if you consider a single particle state at lowest Landau level, then it is presented by this function where z is complex variable, fz is analytical function. And there is also exponential non-analytical factor, which will be important. So, but it's the exact solution of our Schrödinger equation, single particle Schrödinger equation. Then many particle state can be constructed like a Slater determinant. So basically, you take product of these functions and take this. Let's say this function is replaced by the following product: zi minus zj, where these are coordinates of the particles, of electrons, sorry, to the power of m, where 1 over m is filling factor. Okay, so now in this many particle state, which is constructed from these single particle states, you can actually create a defect. You basically introduce the hole, which is called quasi-particle, Laughlin quasi-hole, repel electrons, and the position of this hole is given by a parameter. Psi is just a coordinate of this hole. So this will be Laughlin excitation. So I think this is well known. So now you do more than this. Now we need to extend this microscopic state to this situation to carbene disk, basically. So carbene disk contains a huge hole here, which is macroscopic object. But this can be done by introducing in the center of this disk Laughlin quasi-hole and taking it to the power of capital M, where M is basically square root of M is the radius of this big hole. So it's macroscopic object. So of course, out H also shifts. if you keep finite number of electrons. Then you also can insert flux quantum as let's say single flux in the center of this disk. And there are two effects. You acquire the phase, so electrons acquire the phase. Each electron coordinate acquires the phase, but also it actually repels electrons. So in fact, it can be written as a phase factor times Zi to a certain power. Yes. In this way, you actually extend repel electrons, and you increase this radius of this hole. Next step. In fact, we need to deform this state, this carbonyl disk. First of all, experimentally, it doesn't have such a perfect shape, a symmetric shape. And for instance, you can deform locally with gate voltage, you can deform locally H, and we would like to be able to describe it. Second thing, we would like to describe excitations of the state from the ground state, which are those incompressible deformations of the H. And therefore, we need to introduce certain modification of this function which takes this into account. And in fact, this can be done by using Jürg proposal of 1995 by multiplying this function, Laplace function, by exponential of m omega z, where omega is a meromorphic function, which can be expanded in a Lorentz series. It is such function which is analytical inside this gray region. Okay? So now these coefficients tk will parameterize deformations of the Laplace state.
Sorry, just a
Yes.
question. In a lab, the way to implement this deformation would be to deform the confining potential, deform the magnetic field. What exactly are you
I will
doing?
consider two things. First, locally, you can repel electrons or attract electrons, so you can create a bump locally. This in density, in one-dimensional density, so you can have local deformation with the gate voltage. So instead, you remember those metallic strips which were attached to the edge, where you apply negative or positive potential, where locally actually you deform your edge, and in this way you extend path. So in this is the way to actually observe anomalous. You basically change the length of the path. And then there is an ohmic contact, where extra quasi-particles are localized. There you also need to put charge, which is screened by an ohmic contact. Ohmic contact is big metallic reservoir. So this is effect also described by this.
So in all cases, you're really changing the electrostatic potential, in effect.
Yes. Yeah.
So the fact that the middle wave function there is not analytic in the CIs is of no concern.
Because first of all, it's single-varied function.
So
It's
it's
a single-varied function.
yes, but the reason it was analytic before, as you pointed out, it's the solution of the Schrödinger equation.
Exactly. But now imagine that each solution of Schrödinger equation, single particle solution of Schrödinger equation, requires the phase factor due to singular flux. And this is the effect here. It's not analytical. The phase factor is not analytical function. Okay. Next, we need to learn how to calculate matrix elements. So for such a state. So in fact, it turns out that if we take product of these two wave functions, consider the norm of the wave function, it can be eventually taken all the effects on the previous slide, be written like this. So it can be written actually as a partition function with a Boltzmann factor exponential of minus m with certain energy, which can be viewed as a sum of pair Coulomb interaction potentials. Then all these effects, the background effect, you remember this non-analytical part of the single particle wave function exponential of minus z squared, yeah? So it plays the role of the background charge, in fact. I lead you to electrostatic two-dimensional analogy, and this is like a charge which compensates total charge of quasi-particles, yeah? So then there is a contribution of the central hole. You see that it looks like a certain charge of the certain singular point-like charge because potential is logarithmic, with the total charge equal to m over m, and then this is contribution of deformations, which are parameterized by expanding in a Lorentz series. Okay, so now here you see total integral over all coordinates of electrons. In fact, it can be in large n limit where we have many macroscopic systems. can be written in terms of this density as a functional integral with some correction which disappears in a dynamic limit. Okay. So it can be written as a functional integral, so it actually becomes a partition function of classical Coulomb dimensional plasma. And I think many of you are familiar with this. So now all these other effects like background charge, this charge of the central hole, macroscopic charge, and these deformations play the role of external potential in this free energy of the plasma, classical Coulomb plasma, or Coulomb plasma. Okay, so next thing, we consider dynamic limit. Imagine that we consider such a dynamic limit and take this integral. And in fact, in dynamic limit, we can apply stationary point approximation. Simply, we need to minimize the energy. If we take a variation derivative with respect to density, we obtain the following equation. So the total potential, it can be written like this. The total potential is equal to integral of the density with the Coulomb potential and plus external potential. And it's equal to 0. That's the equation which we obtain by minimizing energy. And it has a very simple physical meaning. So consider such a one-hole object in form of the carbon disk. Inside this gray region, the total potential is 0. So in fact, you have perfect metals with perfect screening. So background charge is screened by electrons in two-dimensional sense. And inside, this equation tells you that inside you have 0 potential, but outside it's a bit. So that's the problem which we need to solve. We need to solve such a two-dimensional problem in order to make a connection between our function omega and our coefficients which parameterize deformation of Laplace state and solution of this two-dimensional equation. So that's the idea. So if we solve it, we substitute back our solution to the free energy or to total energy like this, and we are able to write matrix element or norm of the wave function. Finally, it was a norm of wave function. Using holomorphic structure of this expression, we can replace t by t prime, and then we obtain arbitrary matrix element. So that's the idea. Next step. So how to solve this equation? Basically, you remember that the Lorentz is function in Lorentz series. Yeah, it's like Fourier transform, Fourier expansion. Yeah, so we can do exactly the same for the kernel of this integral equation. We take logarithm and expand it in a Lorentz series like this. And in fact, it contains two parts, this and this, like similarly outside and similarly inside this carbon disk. And then we by substituting this expansion to the integral equation of the previous slide, here, we can solve it because we know external potential in terms of function omega and in terms of coefficient Tk. We finally solve it and find that in fact solution can be written as a certain formula for the density, one-dimensional density on the inner and outer edge of carbon disk. So this is presented by function sigma. So it parameterizes deformation of the edge. So from this we can read off this density by knowing coefficients Tk, which describe deformation of Laplace state. Okay, so we are now able to write Hamiltonian of the system. So far we have not discussed Hamiltonian of the system. Before Hamiltonian, first of all, as I told you, there are two effects of this deformation. First, we can study kind of local deformations of the edge in terms of this parameterization. And second, we can actually introduce excitations above the ground state, which are kind of waves, deformations of the deformations of the edge. Okay, so in terms of local deformation of the edge, imagine that you take this gate here and push electrons like this. If number of electrons is conserved in the system, then of course the outer edge will go like this. So from dashed line to thick line. So total number of electrons is conserved. And in fact, if you solve this equation on the previous slide in terms of deformation, you find that this effect can be represented by the function omega. So what is sigma here? It's just a delta function plus background, because number of electrons is conserved. Delta function plus background. So the total number of electrons doesn't change. Okay. Now this function can be presented as a solution of this two-dimensional Poisson equation. Let me show it on the previous slide. So here on the left-hand side, you write delta function. On the right-hand side, you read off the coefficients and you resum them, and you find that basically the result is trivial. Sorry. It can be presented as a logarithm. So omega is a logarithm. It can be written like this. But it's not exactly a situation which we would like to consider. It's a closed system. We need to consider an open system. Open system consists of ohmic contacts where all the charge goes. In fact, at the end, one can, if you introduce such a bump here or deform the H here, repair an electron here, they accumulate at an ohmic contact. And this is physical input. You just don't know it from just, I mean, it's not important for mathematics, but in order to describe physical reality of this experiment, you remember this disk contains two ohmic contacts on one side and on the other side. So it's energetically not favorable to deform H like this. Excuse me, like this. Instead, H wants to stay constant, unchanged, because it costs a lot of Coulomb energy in order to deform H like this. Instead, extra electrons or quasi-particles will go into ohmic contact, and this is important ingredient of this theory. So in fact, you need to present such deformation by if you deform locally H, you could obtain something like this. But it's easy to do because it's exactly the same effect, but you need to add this effect here and subtract it here. And finally, you obtain the following function for the effect of gate voltage, local gate voltage, in the presence of an ohmic contact. This is true for outer H because there are two ohmic contacts at outer H and inner H. This is true for outer H and inner H. So just remember this formula. So now I can summarize all effects which actually already point towards the direction of resolving this Byers-Young paradox. If you add all the effects which you discussed so far, you can write your total wave function like this. Laplace wave function. This is the effect of inserting single flux. This is effect of changing number of quasi-particles by one. So the m is plus minus 1, etc., plus minus 2, etc. And this is deformations. And deformations are due to local gate here, an ohmic contact here, and an ohmic contact there. And you can write them in this way. All the effects can be written in terms of this function f, which is nothing but a logarithm represented on the previous. And we have coefficients which contain total number of electrons, change of number of quasi-particles, and the effect of singular flux. If you take all this into account, you see that in fact Byers-Young paradox is resolved in the following way. This expression is gauge invariant. For instance, if you change phi by phi naught here, you require a factor 1 of n, or number 1 of n, and this can be now compensated by changing delta m in stationary limit, if you wait long enough, by minus 1. So in fact, this is how in our ground state wave function, Byers-Young is satisfied. It's not the whole story because it's just a ground state wave function. It in fact satisfies the Byers-Young argument. So the conclusion here is that every time phi over phi naught over m has to enter additively with delta m over m. So if you change quasi-particle by 1, or if you change flux by 1 quantum, you have to be able to change quasi-particle by 1, and then the effect is compensated. Okay. So we see. Now, this is so far ground state wave function. We need to introduce a spectrum of excitations of this, which follow from deformations. So, if we substitute our solution of Laplace equation, two-dimensional Laplace equation, to free energy, or to just total energy, we obtain the following expression. Constant plus this bilinear form with coefficients which parameterize deformation of the H.
Excuse me. So far you talk about wave function with different deformation of wave function. And wave function is not related to energy, right? Because it's a variation of wave function.
Yeah.
Now we start to talk about energy. What is definition of F? Is this free energy of Coulomb gas?
Yes.
It's free energy of Coulomb gas?
Two-dimensional Coulomb gas.
Yes.
So
So it's not an
energy. It's not energy.
It's not Hamiltonian, not
It's
energy.
not energy. It's just a matrix element. It turns out to be equal to partition function. Okay. At the moment is just a no.
So normalization factor
Next
of
slide. Yes. Next slide will be about energy. Yeah. Okay. So it turns out that wave function can be actually considered to be a coherent state of certain operator A, which changes let's say, number of excitation. So in fact, one can introduce certain operator A, the eigenvalue of which is proportional to Tk. Okay? Then it turns out that one can also introduce a Dagger operator, conjugated operator, which acts on the left exactly in the same way. You replace Tk by Tk conjugated. But on the other hand, the same result can be obtained by taking derivative with respect to Tk. So if you take derivative with respect to Tk with some number here, it pulls this exponent of the exponential function down, and you will obtain something which is proportional to Tk conjugated. Okay? And in fact, you can express this A Dagger in terms of derivative. And then you can write a commutational relation with such operators. And you find that these are harmonic oscillators, basically. Okay, so remember that now we introduce these operators which are derivatives of Tk or Tks themselves. Similarly, one can introduce zero mode. If you would like to change number of electrons or number of quasi-particles by one, this can be done by vertex operator exponential phi, and the number of electrons and number of quasi-particles are canonically conjugated by. This you introduce by modes, basically, because you would like to change number of quasi-particles and number of electrons. That's where we discuss energy. Now let's introduce energy. So now we have this deformation of one-hole droplet. And we assume that this density, as a result, physical charge density is accumulated, and it interacts with itself via Coulomb potential. So it means that the total Hamiltonian of the system can be written as single particle potential, because of local deformation. You can introduce such a potential by, for instance, introducing gate, etc. And then there is a Coulomb pair potential. So we simply need to calculate, and that's the essence of this step, which is we call rolling projection. So we do not consider all deformations of the system, all states, but just small deformations of the H. Yes.
So one question about the Hamiltonian. So if you forget the confining potential, the U, and you replace a Coulomb by some pseudo potential, it's an exact statement, right? Roughly. So now what's the statement? Because it's not an exact eigenstate, the wave function you wrote, if you take Coulomb.
It's a good question, yes. But it's known that the exact state has a very small difference compared to a numerically found exact state. Has a very small difference compared to Laplace state. Okay? And here we do not discuss this type of physics. What would be internal inside deformation of the quantum Hall state? We consider instead what would be energy cost of deformation of the H. So much smoother. Remember that it's low energy projection. Not only we consider small deformations, but also with a long period. So much longer than distance between electrons. So we do not consider ultraviolet pigment. We assume that it's like a cutoff in our effective theory, but we consider low energy physics, and therefore the question which you ask is related to what happens on a short length scale to our Laplace state. And we say that it's not, it's known that it's not very much different from exact state. So, and this is we ignore, this difference we ignore.
It is not very much different from the true state, even close to the boundary, in the bulk? Sure.
This I don't know. Yeah, it's an interesting question. But imagine something happens on a short length scale. So let's just, I don't know exact answer, yeah? But you are right. So at the H, something strange can happen which is not known to science. But I think that we just ignore this. We think that maybe something happens at ultraviolet energies, and we just don't touch this physics. We consider much weaker effects and on a long landscape. But I mean, I'm not able to answer the question.
Maybe just a slightly simpler question. So let's forget the interaction. I guess this is valid if m equals 1, right? It's just a trivial case, integer, no interaction. Then you wrote an ansatz for the wave function for a deformed droplet. Is that an exact statement? That's an exact eigenstate? Just the u part or not?
For m equals 1?
So just confining potential, no interactions, nu equals 1. You have a wave function, so it's just Slater with this exponential minus.
This is exactly.
Okay, we should we talk tomorrow, but we prove that's not true.
Let's discuss. In fact, let me answer your question. In addition, I have additional remark. In fact, you're absolutely right. Something happens at the edge. This is the big point of our paper. What is known, what happens at the edge, is so-called edge reconstruction. So it means that our paper has certain intuition, certain consequences, etc., but it doesn't discuss physics in all aspects of physics. This edge reconstruction is very important, and in fact, it's still an open question, what happens at the edge. There are experimental proofs that there is an edge reconstruction. For instance, for filling factor 2 over m, you can overshoot of the density, and then it goes down. And nobody knows the exact solution of this theoretical solution, but only effective theory. Like one of these K matrices describes such a state. And then experiment supports this edge reconstruction. There is one more experiment which supports actually much more complicated reconstruction, like one down. So in fact, 4 states. So K matrix is 4-dimensional. So it's an interesting question. Yeah, it's true. But let's start from conjecture that such a wave function, Laplacian wave function exists. Let's see what the effective theory level, what it brings us, and how we actually satisfy Bayes-Young argument. So let's just limit up to this discussion. Okay, so in the next step, we just write this total matrix element projected to low energies to these weak deformations and long wavelength deformations. So I skip these calculations because we know these deformations, we can write them down, we find this matrix element in choice of coefficients tk, and find the following form, Sabellian form. And finally, we can express them in terms of AI characters. So this is how Bosonized Hamiltonian of such small deformations of H, which describe chiral bosons which propagate in clockwise and counterclockwise on our parameters. So if you take this energy and calculate the group velocity of it, then you obtain actually, this is given by this coefficient here, and this is group velocity. So in fact, the Coulomb potential gives you simply denormalizes group velocity, which follows from the confinement potential. So confinement potential gives certain group velocity, and Coulomb interaction adds extra term. And finally, there is also a zero mode contribution here to the total energy. So this zero mode contribution on from the physical point of view, it's the energy of capacitor, basically. So such system has a capacitance. If you charge it, then it has a contribution to the energy. And this is important because, in fact, this is the energy which we'd like to avoid. We don't want to pay this energy. And instead, we insert an ohmic contact which screens this energy. So the actual total charge, by minimizing this energy, we require that there's no total deformation of the H, background kind of average deformation, and then total charge goes to an ohmic contact, the one effect which I mentioned before.
Just a question about the group velocity. You may have mentioned what is d, the log d over LB?
Okay, d is green. So in fact, it's logarithmically divergent. Imagine that your H is close to some piece of metal, some, I don't know, some certain distance to be screened. And here we assume that this distance is smaller than the size of the system.
Right, so it's really material dependent. Very small.
Yeah. So otherwise it's divergent. Okay, so now important part. We need to write a quasi-particle operator. Where this is interesting.
Let's negotiate the timing.
Okay.
How much? Yeah, so how much time you need?
It's just 5 minutes.
Yeah, okay.
I will try to squeeze to 5 minutes. Okay, so let me go a bit fast. So in order to write quasi-particle operator, it's where quasi-particle is removed, for instance, electron is removed, you simply replace one coordinates by parameter in this Laplace state. So then the quasi-particle, so the electron operator requires the following form. So the wave function where one electron is removed is of this form. So the idea to write quasi-particle operator is to write, you take this electron operator to the power of 1 of m. So that m quasi-particles gives you 1 electron. So it's a simple idea. So then we take this to the power of 1 of m. And the problem arises. This extra factor here, it looks like a constant. But it's not single-valued. And it's fine if it's not single-valued, but unfortunately it's not single-valued with respect to quasi-particle number. So eigenvalue of quasi-particle number n. So it's not a good idea. So it's not only single-valued, but also it's just not just a constant which can be actually absorbed in a tunneling amplitude. Okay, so this eventually becomes important. So then the point I think we partially can resolve this problem by taking tunneling operator, where you create quasi-particle and annihilate quasi-particle. So it means that on one edge you remove quasi-particle, on the other edge you insert it. So that in total you don't change number of quasi-particles in your system, and you are not allowed to do because it's made of electrons. Okay, so then you obtain this prefactor. Okay, so what was the role of this prefactor? In fact, it turns out that tunneling operator is not single-valued in a bad sense, because if you have local tunneling like this, you can imagine that these two phase factors will cancel. But then you can move this point around and then go to like this, and go to the other branch of the same quasi-particle operator. Then quasi-particle tunneling operator requires this phase factor, which is an operator. That's what is called plan. The point is that this is, I mean, the only way to resolve it, we're not able to resolve it theoretically just because we do construction. We do not derive this quasi-particle operator, but we construct it. So deriving quasi-particle operator would be to write Hamiltonian of quantum point contact and somehow solving it. We don't know how to do this. That's why such a problem arises. So how do we resolve this problem? We say that this is not allowed. Any quasi-particle operator has to contain only this combination, as I mentioned. For ground state wave function, same applies to quasi-particle operator. It has to be function. It has to be function of m plus phi over phi naught, so that Bayes-Young argument is satisfied. So therefore, all these other branches of this quasi-particle operator are not allowed. So no plane factors. They would violate our limits. Okay, so almost we are approaching to the end of the talk. So now we can combine all the effects which we discussed before. This is our quasi-particle operator, and these are, let's say, this is linear part where we replace t coefficients by creation and annihilation operators A. And this is very familiar form of the effective theory quasi-particle tunneling operator on the effective theory level. So basically it's an expansion with respect to linear expansion with respect to oscillators. Okay. Finally, we need to take into account all the deformations which we discussed before. And you remember that this given by shifting t's by tks. One can explicitly write them in a quasi-particle operator, but on the other hand, we know that a's are proportional to tks, and parametrical shift of coefficients t by, let's say, some parameter which describes deformation of the edge can be directly applied to oscillator operators A. So like this. What is called polaronic shift. If you do this, you obtain final form of quasi-particle operator. So now all the deformations which are parameterized by coefficients tk and which are solution of this two-dimensional electrostatic problem are hidden there in these phase factors. So, excuse me, I'm not used to this pointer. I need to drag it. Yeah, like this. Finally, it's basically the last slide. So this is part of calculations which are maybe boring. Imagine that you now already know tunneling operator. The next step would be to consider transport problem. Imagine that you have a current which flows from one harmonic contact to the other harmonic contact, as shown here on this carbon disk. So what we do, we are not able to solve a problem of coupling such a complicated state to piece of metal, disordered metal, because it's just different states of matter. I think it's theoretically still open question. What we do, we consider weak coupling of anomic contact to the edge, described by tunneling operator, again by electronic tunneling operator, and we write a master equation for the whole system. Here you have weak tunneling, here you have weak tunneling, here weak tunneling, but much stronger than that quantum point contacts, and here you have weak tunneling. So finally, you solve master equation which describes transport of electrons from one harmonic contact to the other harmonic contact. And when you present average current in stationary limit, then it's proportional to this product of tunneling operators for quasi-particles like this, which contains this phase factor, and phi and m enter in the way that Bayes-Nash is satisfied. Then you have to sum over this m number of quasi-particles. Like imagine filling factor 103, you can have inside of carbon disk 1, 2, 3 quasi-particles. You need to sum over all these degenerate states, and eventually these quasi-particle oscillations will disappear. You have zero effect. On the contrary, if you have, for instance, Mach-Zehnder interferometer, not Mach-Zehnder interferometer, but Fabry interferometer shown here, you simply need to put anomic contact on the other side. So you see that in this case you have actually closed loop. So here, sorry, you can go like this. This is Fabry interferometer. Then the argument of Bayes-Nash doesn't apply at all. So because when you thread a single flux here, you do not change flux for this loop. But then, of course, you can observe quasi-particle oscillations, but they are not different from Coulomb plaquette effect. So that's the idea. So I would like to summarize here. So basically, we managed to write low energy theory, effective theory, by doing projection of Laplace quasi-particle state, and take into account all the effects, like topological effects, which are present in carbon disk and Mach-Zehnder interferometers, and also taking carefully into account deformations of the edge. Finally, we obtained the following result, that our theory agrees with, satisfies Bayes-Nash argument. It shows that there is no need to introduce Klein factors because they break Bayes-Nash argument, so you are not allowed to introduce them by hands. And finally, we show that indeed quasi-particle oscillations, this particular model of Mach-Zehnder interferometers, lead to the fact that quasi-particle oscillations in Aronow-Bohm effect disappear. You will see only electronic oscillations, and now it agrees with experimental observation. However, this is true for filling factor 1m. If you consider other fractions like 2m, etc., then Bayes-Nash doesn't apply. And you can have quasi-particle oscillations. And that's what experimentalists are doing right now. And our early theory on spectroscopy of fractional Konokovo effect, Konokovo states, still applies.
Okay. Well, thanks a lot. Possibly some very short question.
Sure, but very short. The more conventional approach, I don't know, one of the approaches is that you don't think about Laughlin function as a bulk, but you just go to chiral boson at the edge and then do construct interferometers from that point. So what extra things you learn from projecting Laughlin's wave function on the edge compared to this purely phenomenological approach?
Okay, so first of all, it's too naive to write quasi-particle. Last remark. Thank you for a very nice question. So, in fact, you are not allowed to introduce Klein factors by hands. That's what our colleagues were doing. That's what we were criticized because we were not doing this. Second, in fact, it turns out that the role of these Klein factors is played by zero modes. You remember that zero mode changes number of quasi-particles, but there is a canonically conjugated part, which is density. And this density depends on position of ohmic contacts and gates, etc. It's not universal, this effect. But it turns out that, and this is a very interesting effect, what happens physically is that when quasi-particle tunnels, it doesn't stay there. Actually, it moves towards the ohmic contact. because it's an extra charge and you don't want to pay this energy. As a result, with group velocity, it moves towards the longer contact, which turns out to be inside the whole loop. And this leads to a certain phase shift to the next quasi-particle operator. Then next quasi-particle tunnels and shifts again phase. And when you solve this master equation, you have to average over these shifts, and it gives you zero effect. So the conclusion is that, I mean, eventually, effectively, because only these combinations, these matrix elements, which contain total number of quasi-particles inside the loop, contribute. Then, it, in some sense, plays the role of the Klein factor. But there is no need to introduce it by hands, and the new idea is that, in fact, the role of Klein factor is played by zero mode, which is not universal, and it depends on system. And if you slightly change the system in a certain sense, then probably you will see some other effect, and quasi-particle oscillations will be restored.
As far as I understand, the Aharonov phase has been measured in a Fabry-Perot experiment, and last year or 2 years ago. I mean, do you want to comment about this, or you don't want to?
Again, so these experiments, there is controversy, always. I mean, of course, somebody claims that Aharonov effect of quasi-particle periods has been measured. Other people will say, no, it's, you can confuse it with Coulomb-Blaquet effect. There was a recent experiment where people have seen quasi-particles localized inside the loop, which do not directly go to omni contact, but localized in some, with some disorder, the quasi-particle localized inside. This leads to phase shift. In this way, you can observe certain quasi-particle number inside and the phase shift. Yes, this experiment exists, and I think, yes, it could be considered as an effect demonstrating an exchange effect, statistical phase of quasi-particles. I agree. Yeah, it's very recent. I think a year or 2 ago.
Okay, people, I think we have to postpone further questions and thank the speaker again.